breakers. Adjustable circuit breakers, guys. We showed you a few things about adjustable circuit breakers. We did SKM coordination. We said if you guys should have this picture too. This is nothing new, nothing to write here. This is a picture that you did, and Chris was thankful enough to actually do it better for me. If you have a Magnum DS power circuit breaker, square D color hammer, this one, you're gonna have four things about every power circuit breaker, guys. And we talked about this one. You're gonna have the frame size, 4,000 amp in this case. You have the sensor size. These are the CT donuts, 3,000 amp. You have the plug size. This is a tiny electronic equipment that you plug right into the face of the circuit breaker. This could be 200 amps. And the bottom, the four, is the settings: a long time pickup, short time pickup, long time delay, short time delay, and instantaneous, plus the ground. We talked about this one in PowerPoint presentation about these, and we did calculation for them. And if you forgot what we did, it's on YouTube. So this presentation also on YouTube. So what I'm going to do today, I'm going to walk you guys through an example that's going to be in the test. The example goes as follows. You're going to see, I'm giving you a frame of a 400 amp, a sensor of a 4,000 amp frame, and a sensor of 3,000 amp, and a plug of 2,000, and I'm asking you to find the following. Everybody's with me? I have a circuit breaker. I bought it. The frame size is 4,000. The sensor size 3,000, and the plug that I'm plugging it at is 2,000, right? Imagine if they come up in this way. And I need you guys to find the following: long time pickup. And I decided single-handedly, Mr. Kurdi, to go put the setting for the long time pickup like we did in SKM. The setting was set at 0.7. I'm setting this circuit breaker at 0.7. And I need you to find the amp setting for this circuit breaker. The amp setting for this circuit breaker. Cool? The amp setting for this circuit breaker. Okay, I told you guys, you have this one. The same example that I told you, you should have it. So I'm asking about long time pickup in amps. The formula that you need to use is always the setting multiplied by the plug amps. What's the plug amps? What's the setting? I'm giving you a setting of 0.7, right? So here's a 0.7 setting. And my plug neck is, what's my plug size? I'm giving you a plug of 2,000. Thank you, sir. 2,000. So if you take 0.7 multiplied by 2,000, what do you get? 1,400 amp. So this circuit breaker, for all practical sizing application, is nothing but 400 amp, 1,400 amp circuit breaker. Does that make sense? Does that make sense? So you need to find the long time pickup, the setting. I'm giving you the setting on the test. You're going to see a setting. You're going to see the frame size, 4,000, the sensor, the plug, all these sizes, and you're supposed to find the actual amp setting. Okay, now the question that you're going to see also on the test, I want you to size the feeder here. I want you to size this feeder. So tell my friend you're going to have 4 amps for the circuit breaker. Which one are you going to be using to size the circuit breaker at? You're going to use the 1,400. 1,400. Trip, when you guys go to Mishad Cooley, if you go to any of your projects at Mishad Cooley, they call the long time pickup trip size. They call them trip size. So the long time pickup or the trip size is what we size the cable based on. Very, very important. Okay, so I want so the first thing, you need to find the amp size for the long time pickup or the trip size. Second, I need you to size the conductor. Chris, in this case, I need to divide by size them. I decided single-handedly, Chad, to use parallel 5 sets. So if you parallel 5 sets, you end up with 280 amps. And if you take this one to 310.15 B16 under 75-degree column, you're going to end up with the following. You're going to end up with 5 sets of, let's do full neutral for this time. Full neutral, 4 conductors, 300 kcm. So on the test, guys, I'm going to ask you first to find the long time pickup, and second to size the cable. So when you look at the circuit breaker is going to have 4 amps, 4 amp rating. one is the frame, one is the sensor, one is the plug, and one is the long time pickup or the trip. When you size the conductor, you always size it based on the trip size or the long time pickup. That's it. The sitting formula, bring it with you. You don't have to memorize it. That's when, if you guys looked at SKM, the one that we did, that's exactly what SKM does. It takes the sittings, multiply it by the plug size. The plug amp, not the sensor amp, not the frame amp. Any question? Any question? Chris, does it make sense? Nick?
Yes.
Okay. Shall we move to the next one? Cool? William? Okay. The second one, guys, is I'm asking you to find the short time pickup. STPU is industry standard for all the analysis that we do. It's called short time pickup. Short time pickup in amps. And Rob, my friend, I decided single-handedly, Mr. Curdy, to put a 10, to sit this one at 10. I will give you this one on a test. I say the settings is set at 10. And I'm asking you to find the STPU, short time pickup in amps. The formula is short time pickup multiplied by the settings multiplied by long time pickup. Okay, what's the settings? The 10. What's the pickup? 1400, right? Long time pickup in amps is 1400. And if you guys do your math on this, you're going to end up with 14K. 14K. So you're going to have 14,000 amp. That's the short circuit, the short circuit or ground fault at which the circuit breaker is going to trip. That's what you're basically short time pickup. Short time pickup is mostly ground fault and low level short circuit. Any question about this, guys? So what you need to do, first write the formula down and then apply the formula. What I will give you is the setting for the long time, the short time pickup is 10. You need to apply the formula. Straightforward, no gimmicks, no math. Any comments, any questions? Number 3, guys, I need instantaneous pickup. Instantaneous pickup, I'm setting it at 20. And I need you to find the instantaneous pickup in amps. That's if all hell break loose and I tied the ends of phase A to phase B to phase C and I flip the switch on. That's the largest amount of current that this circuit breaker will be able to encounter.
So essentially, the bigger the setting,
the more it can handle.
the more.
Yep, absolutely. So so the formula for this one, Nick, is you need to, the instantaneous equals setting multiplied by the plug amps. It's very important, guys, to know which amps. There's so many amps. The plug amps. So in this case, what's the settings that I'm doing it? 20 amps. What's the plug amps? Anybody remember what was the size of the plug? 2000. 2000 is the plug, right? We started with the plug amps. And that will give me 40K. That will give me a 40K. Done. No gimmicks, nothing. No, nothing to it. The last thing I want you guys to do in this example is instantaneous time. I didn't ask about the instantaneous long time delay and short time delay because these are a piece of cake. The delay is always in seconds. So what are you going to calculate in seconds? Either you put it 0.3 seconds, 1 second, 2 seconds. There's nothing to calculate. The long time pickup, short time pickup, instantaneous are the ones that you need to do some math on them. And the software that we use, SKM software, guys, go through the whole calculation for you. Okay, instantaneous. Now, instantaneous time to open the circuit breaker in seconds. I set the instantaneous time. Now this one is the instantaneous amp, pickup is amps, instantaneous to open is in time. I'm setting it at 10 cycles. Instantaneous, guys, they set them as cycles. So I will tell you, if the instantaneous is set at 10 cycles, how many seconds would it take the circuit breaker to trip? That's the question is. Instantaneous is sitting at 10, how many seconds it will take you 10 cycles to trip? So anybody knows, basically, can you convert cycles into seconds? So piece of cake, you're going to take the, how many 10? We have 10 divided by 60. Anybody knows why 60? Because we use 60 cycles in the US. 0.167 seconds. So that's your answer. See how hard of a math is that? Done. So that's basically, it's gonna, you guys gonna have one question related to the setting of an adjustable, electronic adjustable circuit breakers.
So 10 is that in seconds or cycles?
10, I will give you cycles, 10 in cycles,
So it's,
and I'm asking you to convert them to seconds.
okay, so it's the unit of 10 is cycles.
Yep, absolutely.
And the unit of 60 is, no.
10 seconds, 10 cycles is 10 over 60 over second. Because in every 1 second, how many cycles in every 1 second? 60 cycles, guys, is 60 cycles in a second. 60 cycles in a second.
Is that typically how it's set as well?
How do you set it?
Breaker.
How is this a typical setting?
Right.
Back to the coordination. Yes and no.
No, I just mean when you turn something on the device.
Yes, it will be 10, 9, 8.
Cycles, right?
It will be in cycles.
That was it.
Yes. Yes. In cycles. Yes. For the most part. Okay, so that's basically it, guys, in terms of this this example. So I'm going to go save this. I will PDF this and it will be on the network too. So let's close that one. And let's go back to a second example that we have here. And this this one is going to be about fire pumps. You guys were here when we did fire pumps, right? Almost all of you. Fire pumps. Any question guys about finding these 5 things for adjustable circuit breakers? You're going to have a circuit breaker with a frame size, a sensor, a plug, and a settings, and you're supposed to find these little things for it. Any question? Cool. Okay, let's go to the second thing I want to do, guys, is fire pumps. I gave you 2 sheets for fire pumps. You should have these sheets right in front of you when you do the fire pumps. If you don't have these sheets, good luck. So you're going to have these sheets, and you're going to answer. We're going to do 2 examples. One example about, again, the stuff that I'm doing, guys, is going to be PDF and on the network too. So you're going to have 2 examples, one with a transformer and one without transformer. So if you guys look at this, this is the one without the transformer. So I have a generator, a feeder for an auto transfer switch that's going to feed a controller that controls a jockey pump and a fire pump. Everybody's okay with that? Everybody got the material? Okay. We also did this one, this similar example, guys, on a week ago. On the same examples we did them. You guys are supposed to do a homework about each one of them. Most of you submit the homework. Remember, next week is to do the homework on that. And we are going to do this example. So this time I decided to get you the following. All what you need for this system is really, first, the jockey pump. I have a 7.5 horsepower jockey pump and 30 horsepower fire pump, and both of them are running at 480, and I need a code letter J and K. A code letter J and K. And I want you, gentlemen, to size all these, 10 things for this system. 10 things for this system. 10 things for this system. Guys, our job as designers and engineers is to lay out the system. This is part of why they pay us, right? Everybody knows that. You're gonna get from, be it an auto transfer switch that pick the fire alarm system or an auto transfer switch that picks the emergency system. I can't emphasize, we went through this example, the same calculation. All what I did for the review, guys, is basically change the numbers. Okay. On the test, I don't want you guys to have the example in front of you. I want you to have the formulas. All what I want to see in front of you is the sheet, this sheet, right here, that I gave you. Okay, so this example, I have 30 horsepower, 480. Jockey pump is 7.5, fire pump 30. I need to find the following. Number one, guys, is for number one, we need to find, and I'm not going to write the code references because you guys, if you go to number one, the code reference is there. For number one, fire pump branch circuit conductor. So what you need to do for the fire pump to find the branch circuit conductor and everything, I need to go 30. I have the 30 horsepower. You're going to take it to 430.52. We use this one under 480 or 460. You're going to find the 40 amps. The first thing you need to do is find the full load current of this motor. It's a motor, right? The second thing you need to do is multiply to find the branch circuit, multiply the full load current by 1.25. When you multiply it by 1.25, you're going to get up 50 amps, right? Then, when you get your 50 amps, my friend, 50 amps, you're going to take it to 310.15 B16. The lady that got married changed their name, and you're going to get from there number 8 3 conductors. Number 8 3 conductors. We have done 2 examples on this one, guys. They are on YouTube too, if anybody forgot how to do them. And you guys did 2 homeworks for me about this, so it shouldn't be, this is not new information. Any comments, any questions? So that's how you do the branch circuits. The branch circuits.
Now, are we still using that RHW?
Thank you. Let's use an RHW. RHW, RHW conductor.
I know we could read up in the code, but what's the quick fast way of
You can use THHN. Well, if RHW is rated for emergency feeders as an emergency feeder insulation.
So it's kind
But
of
typically you're going to find them. Yeah, it handles more heat.
Okay.
It handles more heat. The insulation. Typically you put them in an EMT conduit. Like we said, all these feeders, guys, by code they have to be outside the building. They have to be buried in 2 inches of concrete, right? The feeders for the emergency system. Can I do THHN on it? Yep. If you put it in an EMT conduit. Yeah, if you're going to be, I mean, THHW, underground, buried, then no problem too. Any question, guys, about the branch circuit? So, on the test, guys, when you have the test, I would like you to emphasize how many of them, which step, with how many, and what the installation that you're using. No neutral. Okay, the second one, we're going to go to the Jockey Pump. The Jockey Pump, guys, piece of cake. You have 7.5 horsepower. Take it to the same table. You're going to get 11 amps, Chris, right? That's in your calculator. You take the 11 amps here, and you're going to multiply 11 by, get you 14 amps. And if you get the 14 amps, what do you think you're going to get? 3 conductors, and how many conductors each one of them? Number 12, RHW. Done. This is sizing a branch circuit for a motor. You guys, if you don't know how to do that, I strongly encourage you to look me in the eye and ask for a refund before you leave Dunwoody in a couple of weeks. So exactly like any other, up to this point, there's nothing new difference between this Jockey Pump and fire pump. No difference between, had these pumps been pumps that pumping water or fans or anything else, same calculation. Installation slightly different. Cool. Any questions, comments? Okay, let's go to number 3. Number 3, guys, we need the controller. And again, these numbers correlate with the sheet that you guys have. Everybody knows that, with the sheet that you have. We have a 30 horsepower. We need to find the controller. For 30 horsepower to find the controller, the first thing we size controllers, guys, from go all the way to number 3, you go to Article 430, will tell you which reference you to the controller. You always size them based on the horsepower and the volt amp. Then you're going to go to Mr. DeWalt and find me an actual NEMA. It's not enough just to size them for us. You have to find a NEMA for them. And if you guys go there, DeWalt 6-3, that will give you NEMA 3. I can't emphasize on the test, the only thing you're going to have is write this one in front of you. NEMA 3. Any comments, any questions? Rob, make sense? Sal, good? Okay. So you're going to find from DeWalt 6-4, NEMA 3. Make sure you know where to go to find these information. Jockey Pump. The Jockey Pump, the same thing, guys. We size it based on horsepower and voltage. DeWalt 6-4. That will give me a NEMA. Anybody? NEMA 1. Thank you, sir. NEMA 1. Chris, do we have an overload on these?
No.
No overload. What does that mean? You want these babies to kill themselves in the process of protecting the building. If you have a fire, you don't worry about overloading a fire pump. They have to die in the line of duty. Sounds official.
Yes.
Okay. Any question, guys, about this? Number 3 and 4. Any question about number 3 and 4? Right, Phil? Okay, controller feeder. Number 5, guys, controller feeder. It will tell you the formula that you need to use is also here in the calculation. I've been using it for a long time, guys, doing this, and I still, without this, I still get lost. You have to go to the code and try to figure out how the code does it. So hopefully this will summarize it for you. Controller feeder. The controller feeder, Chris, my friend, where am I here? Controller feeder, you're going to take the full load amp of the pump plus the jockey pump, the fire pump and the jockey pump. You're going to add them up and go 64. I can't emphasize, first you add them, then you multiply by 1.25. That's different than what we did for typical motors. Typically, we take the fattest, fluffiest amp-wise motor, multiply by 1.25, then we add all the other full load current to it. Here, we have to add them and then multiply. That makes, everybody can see the brackets that we have, parentheses. When you do that, baby, you're going to end up with, then you take the 64 amps, you're going to take it to table 310.15B16. And when you go there, Chris, what do you get? Number six. And let's continue with let's continue with 3 conductors, number 6, RHW.
I don't want to bring up a big topic, but are we pulling ground floor or EMT?
If you put them, thank you. If you put them in the EMT conduit, your EMT will be your equipment grounding conductor. If you don't, then you need to size an equipment grounding conductor based on the overcurrent protection device. No, yeah.
So that would be a gimmick that you can pull.
Really, you guys should know that.
Sorry, I wanted homework on Saturday.
Okay. Homework on Saturday. If you guys have the sheet, follow the presentation, and you don't get an A, ask for refund. ATS, sizing the ATS. When we size the ATS, guys, the ATS, we do the same thing. This is opinion. Everything I say opinion. The ATS is opinion. This is my opinion. And believe it or not, my opinion should count, right? 64. At least for the class. So 64 amps, then you take the 64 amps, guys, that you got, which is basically, we got them up there, to the wall 3-12, Chris, still 3-12 from the year ago. And when you have, what's your next ATS? 100, right? We use disconnects for them, absolutely. Yep, we use, for the sake of the calculation, we use the disconnects sizes as a ATS sizes. Now, might not be exactly the same, but in a real life, you're going to go, typically, they're not far away off, but typically you're going to go to a manufacturer and find what the standard that they use and pick the next standard. Make it easy for you here, standardize it a little bit. 100 amp is a standard. Any question? Dustin, my friend, does it make sense? No? Yes? Okay, so that's basically the ATS that we're going to use. Step number 7, conductor from the service. If you can see, guys, I said same as number 5. And what was number 5? Was 3 conductors. And the insulation, 3 conductors, number 6, right? And RHW insulation. And the same number 8, guys. Number 8 is also the same as number 5 calculation. Number 8, 3 conductors, and that's why Chris said they're the same, Chad. Why are you bothering us? RHW. Bothering you guys because you are in the business of sizing. These could be different as we move on. So we had 7 and 8 and 5 are identical. 7, 8, and 5 are identical. Any question, guys, about this? Sizing it? are identical. No gimmicks, nothing. Now number 9, if you guys go to number 9, this is the overcurrent protection device that's coming out of the line side of the service disconnect means. The line side of a service disconnect means, if you look at the picture right in front of you, by code you have to feed the fire pump from the line side of the service disconnect means. And you have to have an overcurrent protection device for it. And that overcurrent protection device have to be big, fat, and fluffy to handle the locked rotor current. Okay, for this one you have to do a few calculations. Number 1, Nick, you have to go to table 430.7b for K and J, the code letters, and find the locked rotor current for these pumps. We size based on locked rotor current. Okay, so if you guys go to 430.7b and for the K, you should come up with 8.99. 8.99. Now, Nick, when you go there, you're going to find 2 limits, upper and lower limits. Which one do we use? Always go higher. The worst scenario is higher. Thank you. The worst scenario is going to be higher. Multiply this by 30 because we have 30 horsepower for that fire pump. And that will give you 324 amps. So it will give you 324 amps. 324 amps. Same thing for the jockey pump, guys, except the jockey pump is going to be 7.99, if I did that right. And you multiply it by 7.5 and divide by the same voltage because they are, so they'll give you 72 amps for this baby. Cool. So first, step 1, find the locked rotor current for the fire pump. Step 2, find the locked rotor current for the jockey pump. Step 3, add the 2 together. Step 3, add the 2 together. So we're going to have 324 plus 72. And Chris, if you pass the 5th grade, you should be able to come up with 396 amps. 396 amps. And if you take the 396 amps, take it to 240.6 and go up because these are non-adjustable. We're using a non-adjustable circuit breaker on it, so 240.68. If it's adjustable, Chris, I can go, a circuit breaker can go as high as 396 if I can adjust it. We're using non-adjustable on it because it's cheaper, so that will go up to which standard? 400 amp. So the overcurrent protection device is going to be a 400 amp. 400 amp. The overcurrent protection device, guys, is supposed to carry indefinitely the locked rotor current for both the jockey pump and the fire pump for an indefinite amount of time.
Just in case they start really smoking it.
If they smoke, then by the time they smoke, the fire trucks will be pulling in. Right? So your fire pumps does not, the fire pump does not run in your building unless you have a fire. Sprinkler system head got burned, water is going, your fire pump is pumping the pressure, maintaining the pressure in these pipes. That's when they kick in. If you don't have a fire, the only thing that maintains the pressure is that jockey pump, tiny little pump. It keeps running to maintain the pressure right at the sprinkler head. You have to have a certain pressure. And we talked about gas fire pump. Fire pumps are not always required for building, depending on the pressure. If the pressure is, I can't remember what the pressure they have to maintain. If you have to maintain certain pressure. If you can't maintain this certain pressure, that happens in downtown Minneapolis and risers. You have with 4-story buildings and higher. The water can't go all the way to the 5th and 15th story, right? By itself, by the city water pressure, can't go all the way. So what do you need to do? You need to pressurize it to push it all the way to the 18th floor. That's where fire pump becomes handy. Okay, so let's go, guys, to number 10. Number 10 is the overcurrent protection device that's coming out of our emergency generator. And you guys are lucky that I didn't ask you to size the emergency generator. By the way, Tao, if I ask you to size the emergency generator here, everybody knows how to size the emergency generator? We just did size one for us at Dunwoody. They're going to buy one to pick a couple of sump pumps. Everybody knows how to size the generator. Remember common software that we have? You're going to go grab, it's 2 motors, right? Grab 2 motors. You're going to ask me then, Chad, you have the horsepower, right? And the voltage up. And what type of voltage it's going to be an emergency. It's going to be a 480, exactly. For two motors, we size them. Then, the second question, Chad, do you want to start them at the same time? Or you want to start them different times? If they're at the same time, you throw them at one step. If there are different times, what do? You put them at two different steps. Done. And you size the generator for it. No gimmicks, nothing. Okay, so overcurrent protection device for the generator. You take the 40 amps, so 2.5 multiplied. You take the 40 amps. First of all, you need to find the overcurrent protection device for the pump. So what we do is we take the full load amp of the pump multiplied by 2.5 because that's how we size the overcurrent protection device. If it was a motor by itself, then you take the 100 amp and you go size yourself based on 240.6 an actual physical mechanical size. They'll give you 100 amp, right? So first you find the overcurrent protection device for the pump by itself based on assuming it's just a motor. That's step one. Step two, you add that big fat fluffy 100 here to the full load current of the other motor. This is, guys, like sizing overcurrent protection device for a feeder of multiple motors. On the generator side, exactly the same. So that will give you 111 if I did my math right. And from 111, you take it the same thing to 240.6A, and you have to go down because it's a feeder, and that will get you 110, Chris, or less, 110. So we have a 400 amp circuit breaker on the utility side and 110 on the generator side. That drives some people nuts. The code allows you to do that. And those of you who were in the presentation here, we said it's highly unlikely, guys, you're going to have an emergency, and your generator is also running at the same time. So we can handle 110 and overloading your, and also locked rotor current on your pump. So if that happens, you're out of luck, basically. Okay, so this is the first example that we're going to do. The first example, guys, without a fire pump. Without fire pump. Without a transformer. Any question about without transformer? You guys want a quick break before we move into with a transformer? Yes, no? Keep going, Chad? Chris? Keep going? You're good? Everybody's good? Shall we finish it? Okay. The second one, guys, is now we have a transformer. I injected a transformer right between the auto transfer switch and the jockey pump because I want to run them a 208 system, and my system coming to my building is 480. You guys did an example for me, homework. That was a homework example. 480, 208. Same thing. To solve the problem, I need the primary and the secondary of the transformer. I need the horsepower for the two pumps, and I need the code letter for both of them. And what do you have now?
Why would you want to run them at 208 besides that the jockey pump and the fire pump are rated at 208? Is there any other logical reason? Maybe.
If you have a 480,
yeah,
you'll be fooled to use this system. Judgment. If you have a 480 coming to your building, it would be fooled to put a transformer and lower them down to 208, 120. The only thing is if you have a good deal on a fire pump 208 and a fire pump controller and you want to run them.
On a huge building.
Yeah, it could be also a huge building, but a good deal, because if your system is 208, you don't need even a transformer to start with. If the whole system is 208, that's when a smaller building becomes. Your system is 208, then you don't need a transformer because everything is 208. We do the calculation based on the first example, 208. Done. This is when when your system coming to your building is 480, and you single-handedly decided to run the fire pump at a lower voltage. Could it happen? Yes. Is it a good idea? No. If you have a 480, run them at 480. The only thing I can think of is probably have a good deal on a controller fire pump in your building, or the engineers, the mechanical engineers, specify them for whatever reason to run a 208, and I have a 480 system. So what do we do? Huh? Yes, absolutely. So that's why the first method is the rule, really. This one is the exception, if that makes sense. Any question, guys, about these? This is a requirement. Now we're going to go calculate the same thing. These, in this case, if you guys have the sheet that I gave you, there's another sheet that has a transformer. Make sure you have it. This one has, Chris, how many things we need to calculate this? 12 things? 13 things. 13 things in the sheet that you need to calculate. Okay, let's go ahead and do it. I can't emphasize this is PDF. I know it's so hard for you guys probably to write all the stuff that I did here, but I will PDF and put it in the network.
What was our givens again?
The given, yeah, thank you. The given, let's go back to the given. The given are for 8208 transformer, the 3 horsepower, 75 horsepower, and code letter RS. And Chris, remember how the jockey pump is almost 1/10, kind of 1/10 of the fire pump. It's very small compared to the fire pump, but everybody knows that tiny little baby runs to maintain the pressure in the sprinkler system. So it runs a lot of times. I mean, there's fire or no fire. Every time the pressure goes down in the pipe system, that it runs and fills it again, pressurize it, and keep it ready for a fire. When there's a fire, the fire pump will take care of it. Okay, got the info? Dustin, my friend? Okay, let's go ahead and find, for the fire pump, find the following. Typical. The first thing, guys, repeating ourselves over and over. Fire pump is the first, this baby is 75 horsepower. You need to, by now, 430.250. Now we're going to go to 2.8. We went to a voltage 2.8 because the equipment is rated for 2.8. So give you 211 amps, right? The second thing you need to do is multiply it because it's continuous load by 1.25. What do you get? You get 264 amps. And Chris, my friend, with your beautiful calculator that you have been working on for a while now, 264 amps, shoot it to the lady that got married, change her name, 310.15 B16, and that will give you 3 conductors, neck Y3, 3 phase, right? Do we need a neutral for that boy? No.
I think so.
No neutrals. And if you guys do a calculation on this one, would that be 300?
Yeah.
Thank you. 300 KCM. 300 KCM. That's it. No gimmicks, nothing. Branch circuit for a motor. Branch circuit for a motor. Any comments, any questions? Rob, it's Friday. I know it's Friday, man. To the gen? Okay. All right, so let's go to the jockey pump. That baby jockey pump. For the jockey pump, I have 3 horsepower, guys. Same table, same voltage, so I can get 10.6 amps out of that baby. You multiply by 125 because continuous load, get you 13 amps. Out of the 13 amps, you take it to table 310.15 B16. Anybody knows why we go to 75 amp, 75 column 75, not 60, even though we're less than 100? They're motors. Guys, when you deal with the 3-phase equipment, 99.9% of the time, the logs are rated for 75 and we size based on 75. If you're dealing with single-phase equipment, then the 100 and less becomes a big rule. If the equipment is 100 or less, 60, more than 100, 75, except for motors, even single-phase motors. Okay, so this will be 3 conductors, Chris, and can I get away with number 14?
Yeah.
If you put number 14, I will give you wrong, regardless of what the code say. We're designers. We don't put a wire, single wire, in a commercial building less than number 12. Careless, horse whipping. Number 12. Why? Voltage drop. It's not worth it to pull a stranded conductor number 14 for any load, especially 3-phase, or single phase even in a commercial industrial building. Number 12. So our minimum, guys, when we go commercial industrial is what? Number 12. Only residential that we deal with number 14. Okay. Any question about the jockey pump, William, my friend? Does it make sense?
Yeah.
What's the M stands for?
Minnesota Twins.
Oh, twins. Oops. We forgot that we're in Minnesota here. That's a dumb question, huh?
Hey, Jackson, what your shirt say? Minnesota Twins. You guys match.
We planned it out this morning.
Okay. Pull you back together, Dick.
Sorry.
Pull you back together.
Go back. It's NEMA
Hold
0 and NEMA 5.
Oh my God, Milwaukee have a 0?
Yeah.
Might as well just, thank you, Nick, you're right on the money, man. 75 horsepower, 2.8. I can't emphasize, thank you for going to 2.8. Now we're going to a different voltage. And that will give you NEMA 5, thank you, Nick. And the same thing, Jockey Pump, guys, that baby tiny little boy, that will give you NEMA 0 based on my feedback from my friend Nick. Now, could I use a soft start on these babies? Yes, I could use a soft start. Should I use a VFD? Would it make sense to use a VFD in a fire pump? Do you really want to speed control the fire pump? I mean, I don't know, maybe there's something that I don't know. But soft start, really good. Yeah, you probably would put a soft start on that, where you can ramp that thing up when it comes and ramp it down with some control. But VFDs, I've never seen it with VFD. Soft start is coming, and other auto transformers coming, guys, on these. Or NEMAs, or just across the line NEMAs. Okay, controller feeder. Controller feeder, what you guys do is you take the full load amp of the pump, add to it the full load amp of the jockey pump. That will give you 277 amps. And if you take 277 amps, guys, you take the 277 amps, and you take this one to table 310.15B16, you are going to end up with 3 conductors. Each one of them is how many? 300 kcm, RHW, kcm. Any question about number 5? Any question about number 5? Piece of cake. Any question about number 5? Move on, Chad. We got it. Okay, my friend? We're good? Okay. Let's go to the transformer sizing. This is where now we decided to make a transformer size. To size the transformer, guys, step 6, if you go to your rules, it says you add up the 2 amps for the 2 babies that you have, and you multiply them by 1.25, which gives you the same thing, 277. Then you use 277 to find the kVA of that fat, fluffy transformer that you need to do. So if you do this math, I hope by now you know. I hope by now, guys, you're almost graduating. I hope by now everybody knows how to find the amp and the kVA. If I give you a kVA, you find the amps and so forth from a 3-phase system. That's all what we do. These are the alphabets of the electrical design and electrical construction, right? Volt amps. That will get you 99.9 if I did my math right. So 99.9 transfer into 100 kVA. Where do I find the standard 3-phase 480 208 transformers? It's not enough, guys, to do the math for us. We are required to put actual material. Actual material is DeWalt 7-7, or you can use to Color Hammer Consultant. Beautiful consulting guide, Color Hammer. If you work in an engineering firm or high-profile electrical contractor and you don't have this one in the front of you, and if you want to continue, a horse whipping. That's a big deal if you want to get into the design. Or you can contact Nick, and Nick will size it for you for a fee.
$100 a minute.
A minute?
Yes.
Oh my God, Nick, you're so expensive. Okay, so that's the size of a transformer that we decided to do based on the code. And I don't write the code references, guys, because you have them on a sheet in front of you.
Sure.
So just to expedite the process. Okay, now the second thing, Nick, getting excited before the holiday, huh?
Yes.
Primary overcurrent for the transformer. We need to find the primary overcurrent, no secondary for the transformer. We don't put secondary, we need the primary. Primary overcurrent protection device for the transformer. The way they do the primary, guys, the first thing you need to do is find the locked rotor current. So locked rotor current for the fire pump and the jockey pump based on code letter, what was the code letter that we gave you guys?
second check. If we're doing a primary, shouldn't the voltage be 480 instead of 208?
Yes, but here, can you see where we will transfer this one later on? We are on the secondary side yet.
Okay.
Right now, we're doing the math on the secondary.
Block rotor.
Yep, and we're shifting it via the voltage ratio to the primary. Just hold your horses a second. We are, because the pumps are tied to where? To the secondary. So you do the math on the secondary because the pumps are 2A. So based on the lock rotor that I gave you guys for this particular example, which is R and S, based on a lock rotor of S, you're going to find 17.99. You multiply this baby by 75. Do the math on this. The formula is there. You're going to end up with, oh boy, 3749. 3,749 amps is the locked rotor current on this baby. That's a lot of amps. The locked rotor current. It's an S. Is that the S? That's the S letter coded. Yep, the fire pump is an S. S could stand for stupid or smart, or symbol, or whatever you would call it. So that's a lot of locked rotor current. Almost short circuit value. The baby one, guys, was an R. The R is 15.99. Don't ask me if they ever put an S on these. I'm just throwing these numbers. They will never put an S on that. So you multiply by this, they'll get you 133 amps. So we find, step 1, find the locked rotor current for the fire pump. Step 2, the locked rotor current for the jockey pump, exactly like we did for the first example. Step 3, add them up. Up to this time, guys, it's nothing, no gimmicks for it. Up to 3, then we add them up. 3, 7, 4, 9, add it to 133, and that will get me 3882 amps, right? Add them up, locked rotor. This is the step that's kind of an interesting. The second, so we add them up to step number 3, guys, straightforward. Step number 4, when you add them up, then you take the 3882. Now, Nick, I want you to wake up. I know you're up. Then, now up to this point, guys, we are on the secondary. Up to 3,088, 3,882. These are amps on the secondary. I want to shift them to the primary because I'm sizing primary. So how do you shift an amp from the secondary of a transformer to the primary? You multiply it by the voltage ratio, right? Because you know the rules of a transformer. Rules of a transformer. Voltage up, current down on one side of a transformer. Okay, so you have to divide them by the voltage ratio, secondary to primary, which is 2.8 divided by 4.8. Now we're talking. Now we scaled, Nick, this is where you scale down the amps to move it to the primary, basically, because the voltage is high. You accommodate for the voltage. Okay? Then at this point, you end up with 1682 amps. 1682 amps. Now, you take yourself to 1682 amps. Now we're going to size based on 240.A. I can't emphasize. You take the 1682, guys, get 240.6A. A is non-adjustable. If they're adjustable, Allah was not here. I can't pick on him today. If they're adjustable, Nick, then what you can do, you can use the long time pickup and tweak it down to get you 1682. Cool. But since they're not adjustable, you have to go up to the next standard. What's the next standard? 2000. In real life, here's what happened. You rarely, I don't think they ever even make a 2000 amp non-adjustable. It doesn't exist. So you're going to have a 2000 amp adjustable. This is what you're going to do. When you get the 2000 amp adjustable, you're going to tweak it down with a long time pickup, set it up at, if you take...
Apply a fuse for that?
Absolutely.
Yeah, here.
Yes.
Well, fuses.
Yes. But then you have to have a disconnect and disconnect fuse and so forth. I believe so. I believe you can put a fuse circuit breaker. Most of the circuit breakers, I believe you can put fuse. I can't recall.
Huge fuses at that place we toured. The
Right.
It was scientific.
Yeah. So if you, Chris, if you divide the amps that you came up with the circuit breaker you got, it gets you 0.8. So if I want to tweak this one, I can go tweak this one actually 0.84. So I have to go up on these. So if I set it at 0.9, then it will give me very close to, if you set this one at 0.9 times 2,000, do I really need a calculator for this? I'll give you 1,800. You set it at 0.9, good to go. You can't set it at 0.95, so 0.9. Okay, we are sizing based on non-adjustable, so we're good to go. Any question, guys, before I move into step number 8? Step number 8. Come, my friend. Cool?
So
Okay.
Are we going to take the actual amps?
Now we're going to size the primary conductor. We size the overcurrent protection device. Now we're going to size the primary conductor. The primary conductor, which is number 8. The primary conductor, you're going to find the actual amps, which is a 1000 kVA transformer. The full load amp for it is 120 amps. Okay. Now do me a favor here. I need somebody to do the math because I didn't do the math. Then I did it differently from time to time, guys. Sometimes I multiply by 1.25. This is really opinion because it's continuous load. Sometimes I don't. But get into the habit being an engineer, we don't pay for the copper anyway, right? So we dump that copper there. So you're going to take 1.25, multiply it by, let's do this step here. So what I do is take 1.25, multiply it by 120. I need a calculator here.
150?
150, thank you, sir. 150 amp. Then you take the 150 and take the 150 and go to the table. That'll give you 3 conductors. I need somebody here because I changed my number. 150. What do you guys come up with?
Number
150. So 150. 1 aught. 1 aught. Thank you. So your conductor here would be 1 aught. Number 1 aught. Number 1 aught. What I do, guys, for the ATS, we'll do the same thing for the ATS. We size our ATS to match the conductor, basically. So I'm going to take the I primary, which is 120, and do another step here. 120 multiplied by 1.25 equal 150. Press. So you take the 150 to DeWalt 312. Do you get 200? You get 200, right?
Yeah.
200 amp. You got a 200 amp auto transfer switch. 200 amp auto transfer switch. So my auto transfer switch is 200. So go buy yourself a 200 amp auto transfer switch. Guys, sometimes the 1.25 here have to have a disclaimer. Sometimes I do it, sometimes I don't. Because remember, Chris, we already multiplied by 1.25 when we sized the.
So
is a lot of overset.
Is it alright if we just do it once? Well,
I used to do it once, but people lean on a lot on the side of safety and blah blah blah. You're safer if you do 1.25. Put it this way. So let's do it this way. Okay. All right. So let's go to step. This is the auto transfer switch. We size my auto transfer switch. Let's go to the conductor from the main service. The conductor. If you guys look at the conductor coming from the main service, that's number 10. That's exactly like number 8. So same as number 8, and which was 3 conductors. Neck 1 aught.
yes.
Thank you. 3 conductors 1 aught. That will be 3 conductors 1 aught. And the second one, guys, is. The second is the conductor from the generator, same as number 8. So that would be 3 conductors of how many? 1 aught. 3 conductors 1-0. 1 aught. 3 conductors 1 aught. Any question, guys, about 10 and 11? Any question about 10 and 11? Straightforward. Okay, you go to number 12. Now, number 12, guys, based on the stuff, it's the overcurrent protection device on that's coming out of the utility side. So that would be same as number 7. And what was number 7? 2000 amp. So here's my question for you. Then do I need actually number 7? Most likely you wouldn't need number 7. You just put 1 at the service, a service, 1, and you do not need number 7, step number 7. So that's 2000 amps. But I would like you to get into the habit of sizing it anyway. Number 13, guys, you need to size the overcurrent protection device on the generator side. The overcurrent protection device on the generator side. So on the generator side, the gen side, I take the 120 full load amp, the primary full load amp. Remember that primary full load amp? Multiply it by 1.25. That's coming from 450.3b, the table for the transformer. So you take it, you multiply by 120. That'll give you 150, Chris, right? We just did that one a second ago. And you take the 150 here, and you send it to 240.6, which is. Who that?
You gotta go to the back.
Oh. So you take it to 150, take it to 150, take the 150 to 240.6, and anybody knows why I start throwing A these days. In the past, I've never threw A. A is non-adjustable. So you get yourself a non-adjustable 150. 150 goes in 150 anyway, so you hit the jackpot, so we don't need to mess with it. Any question, gentlemen and lady?
I just thought plastic's okay.
You'll be all right. Any question? Okay, so let's take 5 minutes break and I'll review for the theory.
Dustin.